Welcome to ShowOffer.io. Today's topic is how to design a distributed job scheduler. And this is a frequently asked interview questions in the recent years. In today's content, we're going to use a playlist to start a fundamental design with scalability and fault tolerance optimization as our primary video. And we will generate incremental short videos for specific deep dive topics. Now, let's jump on to Job Scheduler. What are the use cases you can map to Job Scheduler? According to our ShowOffer materials, we already covered a lot of specific design questions. For example, Slack find out new messages to group chat offline users, or web crawler to fetch, extract, and persist web contents, or YouTube to send email campaigns to subscribers. Job Scheduler is widely used as a pure backend system to support large-scale executions for both scheduled and ad hoc or one-time and recurring jobs. Before we jump into the structure of the delivery framework, we will challenge you with some interview questions. You can use these questions to test yourself if you can answer them if they are asked during your interviews. Question number 1. Do you know how to safely schedule 10K jobs per second, like Slack find out notifications? Question number 2. Do you know how scheduler and queue design mitigate tiny gap between schedule time and actual execution time? This is critical for ad auctions or stock trades at market open. Question number 3. Do you know how to guarantee the right delivery semantics, at least once versus exactly once, in systems like YouTube email campaigns or Stripe payment retries? Question number 4. Do you know how to handle dependencies and multi-step pipelines, such as Airflow ETL workflows in data warehouses or payment processing flows that must debit before credit? Question number 5. Do you know what happens if a 6-hour-long job crashes halfway through, like ML model training or a large-scale analytics backfill? Please bring these questions tightly with you, and we can jump into our today's video. Now let's first talk about the requirements. As for the functional requirement, they are pretty straightforward. Functional requirement number 1, immediate execution. The scheduler must support run now jobs. These are tasks that should begin execution as soon as they are submitted. No delays, no time math, just the in-queue and go. Functional requirement number 2, future and recurring execution. Of course, not all jobs are ad hoc. The system must also support jobs scheduled in the future or on occurring patterns, like every Monday at 8 a.m. or run this ETL job at midnight UTC. Functional requirement number 3, observability. A production-grade job scheduler isn't a black box. The system must provide visibility into overall health, including queue depths, success or error rate, latency, and worker status. Now let's chat about the non-functional requirements. High scalability. The system must scale to 10K job executions per second. This isn't just about the throughput. It is about the distributed coordination at scale. Low latency. For time-sensitive tasks like auctions or payments, we expect jobs to be picked up and executed within 2 seconds of their scheduled time. Correctness. Execution must be at least once by default, meaning jobs will not be lost, but delivery semantics should be configurable. Some workflows need exact once guarantees, others can live with at most once, and the system must support both where they need it. High availability. The system should favor availability over strict consistency. It must stay responsive, even in the face of worker restarts, DB failovers, or region-level outages. Fault tolerance. Workers may crash, networks may flick, tasks may fail. A resilient scheduler must recover gracefully, with automatic retries, failover support, and no data loss. So here is the ramp up of all functional and non-functional requirements on the screen. In a distributed job scheduler system, we deal with two fundamental entities. The first entity, the job. A job is a reusable definition of the work. Think of it like a blueprint. It defines what needs to be done, like send a weekly summary email or generate a sales report. But it doesn't specify when to do it or for whom. The second entity, the job run. A job run is a specific execution instance of that job, scheduled with a timestamp, inputs, and parameters. Using the same earlier example, the job might be generate a sales report. A job run would be generate the Q2 2025 report at 6 a.m. on Monday. This separation is critical because one job may have many job runs across time, tenants, or configurations. In practice, jobs change rarely, but runs are created all the time, and they drive most of the system's write traffic. Here is one quick note for the interviews. Some companies might call these entities differently, like task and attempt, or schedule and execution. That is okay. What matters is that you explain the separation, the definition of work, and the individual attempt to execute it. So in this video, we'll constantly use the term job and job run, and every major design decision will map back to this structure. Now let's come to our high-level design. In this part, we will map each of the functional requirements to a workflow diagram, link the building blocks as well as the necessary data schema to illustrate how those functions can be satisfied by this diagram. Let's start with the immediate jobs to establish the core loop of a scheduler. Because the job should run as soon as it's created, you avoid clocks or colon math and focus on the fundamentals, which in future you will reuse for the delayed or recurred work. And at the high level, this is the stage by stage. Record the intent, enqueue, lease, execute, record outcome, retry if needed. Let's take a closer look from the diagram to illustrate each stage. Step 1. Input arrives. Let's say a request comes in, no runnet, no cron. That means this job should be executed immediately, and this defines the intent only, nothing executes yet. Step 2. Validates and normalizes. The scheduler authenticates the request, assigns a job ID, and sets schedule type equals to immediate. So the downstream components know this job is eligible right away. Step 3. Automatically record job and job run entity. In a single atomic transaction, the system writes a new row to the jobs table describing what to run, and a new row in job run describing the specific attempt with status equals to queued and available at equals to now. This guarantees safety. If the system crashes, we either have both records or nothing. Step 4. Enqueue for execution. This connects DB to workers. As soon as the run exists and is eligible, the scheduler publishes a message to the job queue. Now workers can discover the work without polling the DB. And then we enter the execution part. Step 5. Worker claims and executes. Let's say a single worker at a time and the worker pulls the job from the queue. Before running it, the worker must secure a lease, which is a time-bounded exclusive lock, so no other worker can execute the same job at the same time. Once the lease is held, the worker transfers the job from queued to running status and then begins the execution. We will go back to talk more about the lease shortly after the whole process. Step number 6. Finish and retry. On job completion success, the worker marks the job run succeeded. On retriable failure, the worker records the failed status, creates a new job run with an increased backoff available at in the future, and re-enqueues. This preserves the original intent while keeping each attempt audible. To mention, the exact same loop works for future or recurred job situations. Only available at changes, which is now versus later. That's why we're starting with the immediate cleanly sets for the foundation. Now let's come back a little bit on the lists. Why do we need lists? There are two big reasons. First, to prevent the double execution. We don't want two workers sending the same email or charging the same credit card twice. Second, for automatic recovery. If a worker crashes or stalls, the lease will expire, and another worker can safely retry the job. And here is how it works in practice. A worker claims the job, and it updates the DB to mark itself as an owner, and sets a lease expiry timestamp. For long-running jobs, the worker must renew the lease by sending the heartbeats, like, I'm still alive, don't give my job to someone else. Once the job finishes, whether it succeeds or fails, the worker updates the final status and releases the lease. But if the worker crashes or stops heartbeating, the lease expires, and the backup worker can rescue the job safely. So you may also wonder, where does the lease live? In SQL-based schedulers, it's part of the job runs table, fields like claimed by and the lease expires at. In message queues, it is a built-in, usually called a visibility timeout. Unacknowledged message reappear when the timeout hits. So in short, lists make sure jobs run once, recover automatically, and scale safely, even if your infrastructure isn't perfect. Now let's take a deeper look into what data schema should look like to support our functional requirement number 1. At the core of the system, there are two tables, jobs and job runs. The jobs table stores the definition of the job, what task is, its payload, schedule type, and priority. This table rarely changes. It is the blueprint for execution. The job runs table tracks each execution attempt. One job can have many runs, for retries, recurring schedules, or different tenants. And this table records the full lifecycle of a run. Why there are two tables? Because queues are transient. Once a message is consumed, it is gone. But you need a system of record to track retries, audit execution history, and enforce correctness at scale. That's what job runs give you, a persistent execution log that is traceable and recoverable. Here we recommend using a relational database like Postgres or MySQL as the source of truth for both tables. The reason is, it is ACID transaction to write jobs and run atomically. It has the foreign keys for lineage. It has partial indexes for hall paths like status equals to queued, and also safe parallel claiming using the syntax like select for update skip locked. On the other hand, no SQL system like Redis or DynamoDB are great for ephemeral coordinations, things like the leases or rate limits, but they are not ideal for long-term tracking, consistency, or debugging. So keep your job and job runs in SQL and let your queue handle the delivery. Now that the scheduler reliably handles the immediate jobs, the next step is to add a schedule layer, running at a specific time or on a cadence. The fundamental strategy here is to use DB-driven scan. We can run a small scheduler that repeatedly scans for active schedules with the next fire at column in job table within a short time window, for example, 2 to 5 minutes. For each schedule, it materializes exactly one occurrence in the job run table and advances on the next fire at column. We can refer to the high-level diagram here to illustrate step by step. Step 1. Scan due jobs. Read active rows where next fire at is smaller than the null time plus the horizon time. ordered by the next fire at. This yields a time-ordered slice of what could fire soon. Step 2. Pre-process in small fair batches. Process due jobs, like deciding what exactly should fire, when and whether it is allowed, before pushing them to the queue is a great discussion topic to demonstrate the industry experiences. Step 3. Advance the schedule. For each processed row, compute the next fire at from the last scheduled fire. If further occurrences still fall within the horizon, they will be picked on subsequent job scan. Step 4. Publish to the job queue. This is not straightforward, as there can be multiple strategies during your interview. We will come back shortly. Step 5. Workers execute and close the loop. Workers list by run ID, recheck the eligibility, cancel flags, run idempotently, and write a terminal state. On retriable failure, create a new job run with exponential backoff, available at, and re-in queue. Acknowledge only after durable state is recorded. Now let's come back to discuss 3 strategies to trigger job execution in step 4, and how to choose the right one for a system. Option 1. Direct publish. This is the simplest approach. As soon as the job becomes ready, just push it to the queue. It works fine if your timing doesn't have to be perfect. For the precise workflows, like auctions or financial systems, workers need to double-check that it is actual time to run the job, using the available at timestamp. Think of it as fire and hope, quick and easy, but not guaranteed to be precise. Option 2. Native delay. So let the queue to handle it. If your queue supports per message delays, like AWS SQS or Google PubSub, you can publish the job right away, but tell the broker to hold it until it's due. This gives better timing accuracy. The queue becomes the timer, but it still depends on the broker's delay granularity, SLA granularities, and max delay limits. Option 3. Outbox with relay, and this one is the most sophisticated one. Here, jobs aren't published directly. Instead, they are first written to a local outbox table inside your database, in the same transaction as your job record. This ensures atomicity. Either both the job and outbox are written, or neither. Then, a separate lightweight process called a relay scans the outbox and publishes job only when their available at time has arrived. This option is broker agnostic, supports retries and jitter, and gives you fine-grained control over execution timing. Plus, if you need to cancel or reschedule a job, you just update or delete the outbox row before it's sent. So what about the trade-off? You need to operate and monitor the relay component, but it's well worth for systems that need precise, safe, and scalable delivery. Now let's come into the system health monitor function. Monitoring the system health lets you spot the problem before users do. It keeps the SLOs honest and fix the issues fast by pinpointing where lag or errors occur across the scheduler, to outbox relay, to queue, to workers, and to DB. It guides auto-scaling and cost control, protects the correctness. Let's check on the diagram to see what to measure and where to instrument. So regarding to what to measure, here are some of the examples I pasted here in the screen. They can be scheduling lag, the start lag, the outbox backlog, or the retry funnel. You can take a look from their definitions and what it measures. In terms of where to instrument, especially the single span per stage, I think from the scheduler, from the job run, and the outbox relay, from the queues, from the workers, as well as from the DB side, we listed those definitions and columns that can be tracked. And here's how we use the metrics to show the system health as well. The workflow of the view, for example, scheduling lag to the start lag to the runtime, can tell you whether the delays are at the time gate or at the pickup or the execution. For the capacity view, for example, the queue depths, worker concurrencies, CPU memory utilizations drives the auto scaling and partition balancing. For the stability view, like the job run or even the outbox backlog, publish errors, redeliveries, least secures, or dead queue reasons, those flags the relay or broker issues, bad leases, or poison jobs. After the high-level design, here comes to our deep dives. Let's first talk about how to support large scale of jobs. Imagine your system needs to handle 10K job executions per second. That means your backend needs to process 20K to 30K database writes per second, just to handle the job creation, leasing, and completion events. To scale to that level, you need to improve at least the 3 parts of your system really well. Let's walk through them. First, job metadata and database. Every job gets written, leased, and marked completed. That's 2 to 3 touches per job. To keep it up, you can index your hot paths, especially the available at and status equals to queued, so the workers can quickly find jobs to run. You can also partition the data, for example, by time or by job ID, so that you can drop old data without expensive table scans. You can also use a relational database like Postgres or MySQLDB, not for queuing, but as your system of the record for traceability, retries, and analytics. Second, publishing jobs without duplicates. Now imagine you are publishing jobs to the queue. What if 2 scheduler replicas accidentally publish the same job? That could happen, especially at scale. Here are 2 ways to prevent the duplicate submissions. Option 1, lease-based sharding. Only one scheduler node gets permission to submit jobs from a certain shard. That permission, called a lease, expires if the node dies and another node takes over. Option 2, workers double-check. Even if a duplicate gets published, the worker rechecks all conditions before running the job. Has it already run? Is it still eligible? Has it been cancelled? Here's a pro tip. Combine both options, lease-based scheduling and defensive execution. For the forecast and the safest way, most scalable solution. Number 3, queue and worker cluster optimization. Your job queue and worker pool must scale together. Use hundreds of queue partitions, say 512 or 10,024, to avoid bottlenecks. Auto-scale your workers based on the incoming job rate and average job runtime. A good rule of thumb is jobs per second times average job duration plus 20 to 30% buffer for retries and traffic bursts. But here is the tricky part. What if one tenant sends 10 or 100,000 jobs at once? You need fairness and isolation. Here are a few smart strategies. So priority queues. Let urgent jobs go first, but raise low priority jobs over time to avoid starvation. Concurrency lanes. Use the concurrency key to limit how many jobs from one user or type can run in parallel. Burst smoothing. Add a little jitter to job release time to avoid spikes, especially when a cron job fans out to 10 or 100,000 notifications. Fair batching. Process jobs in small round-robin batches across tenants so no one hogs the queue. But we can see the trade-offs, the consistency versus throughput. If you strictly serialize job per K, like per user or per video, you get perfect order, but low throughput. If you allow limited concurrency per key, you can scale higher, but must make your job idempotent and guard for the side effects. The takeaway here is tune this per job type. Some jobs need strict guarantees, and others just need the speed. Now let's talk about the second deep dive, the fault tolerance. Because in distributed system, failure isn't a possibility, it is a certainty. Machines crash, workers get killed, queues lose messages, and networks occasionally drop packets. If we don't prepare for these, jobs will be dropped silently, or worse, get executed twice. That's why fault tolerance and smart retry strategies are non-negotiable in production schedulers. So, how do we build a system that survives failure without duplicating work or overwhelming itself? We should start with the retry model. The building block here is the job run. Every execution attempt gets its own record, and we design each one to survive retries safely. To do that, we make sure every run has a unique identity, so we always trace it back to the original job ID, an attempt counter, so we know if this is a first try or a retry. And most importantly, idempotency. This means downstream systems, APIs, DBs, anything with side effects will behave correctly even if the same job runs twice. Here is a pro tip. Use an idempotent key like job ID plus scheduled at and pass it downstream. That's how you keep tries safely. So why retry controls matter? If you retry blindly, you risk infinite loops. You can swarm downstream services with flaws of duplicate traffic, and you will file your system with the zombie jobs that no one understands. But with the smart retries, you get resilience to transient errors, predictability under the load, and clarity into which jobs were actually salvaged. Services, those are failed for good. In terms of that, let's break it down with 3 layers of retry control. First layer, backoff and jitter. We don't retry immediately. Instead, we wait and increase the wait time each time. That is exponential backoff. 1 second, 2 seconds, 4, 8, 16, etc. But we also add jitter, the randomness, to avoid a retry stampede where thousands of workers wake up at once and slam the same endpoint. And here's a bonus point. You can also cap the backoff for latency sensitive jobs, say no more than 1 minute between the retries. Second, retry budget. We don't retry forever. You can always set a maximum number of attempts, like 3 or 5, or a time budget, like give up after 15 minutes. Once the budget is exhausted, the job is marked as a give up or sent to a dead letter queue. This keeps your system clean and lets humans step in when automation fails. Third, failure classification. Not all failures are created equal. Some should be retried, others definitely should not. Here's the rule of thumb. For the retryables, such as timeouts, 500s, worker crashes, so these are usually the temporary ones. For the non-retryables, such as the bad input, validation errors, 400s, so this will never succeed, no matter how many times you retry. By tagging and classifying this correctly, you prevented wasted retries that burn CPU and clutter your logs. So we need to model the retries cleanly. Each retry should be its own job run record, with a new run ID, with an incremented attempt count, and a clear state transition, failed to scheduled, then eventually running to succeeded or failed. This keeps a full audit trail, so you can answer questions like, how many times did this job fail? Why was it retried? What fixed it? That's gold for debugging and dashboards. So in short, failure is inevitable, but with smart design, you can make retries your system's superpower, not its downfall. Now here comes to the recap. In our today's video, we walk through how to design a scalable, fault-tolerant job scheduler, covering immediate and scheduled jobs, listings, retries, observability, and scaling to 10,000 executions per second. We will add incremental content into the same playlist to answer deep dive improvement questions, such as long-running jobs, multi-step task runs, etc. If you are preparing for system design interviews or behavioral rounds, check out ShowOffer.io. We offer expert coaching, mocking, and real-world frameworks to help you succeed. Don't forget to like, subscribe, and share this video to someone who is preparing too. More deep dives coming soon.